Yours.
Thank you very much, and welcome everyone to the first session. We have 4 papers in this session. We can move immediately to the first one. It's my great pleasure to introduce Miklos Telek, who's a professor at Budapest University of Technology and Economics. Miklos has been for many years a leader in the community through his stochastic modeling work, and recently there have been some work on matrix exponential distributions in Budapest, which personally I regard as fundamentally important. So we'll see a bit today about this line of work. So Miklos, I will make you a presenter, and feel free to start your presentation. The title of the talk is the CME method, efficient numerical inverse Laplace transformations with concentrated matrix exponential distribution.
Thank you very much. Can you hear me?
We do.
You see also the slide?
Yep.
Okay. So, yeah, I think it is going to be a kind of marketing talk. So I'd like to advertise this method, which is renamed as CME, and I found the title to be too long and too scientific. So maybe it would be better to say that CME method is I would say the up-to-date, simple and reliable numerical inverse Laplace transformation tool. Yeah, this is a very long process, and the current submission is authored by Szala, Aldin Al-Musa, Gábor Horváth, Illés Horváth, András Mészáros, and myself. And yeah, we have got very limited time, but I think many researchers in our field had got the impression that numerical inverse Laplace transformation is something, a mysterious thing, which provides very strange behavior, numerically sensitive, and there is this problem of Gibbs oscillation, which results in inverse Laplace numbers, which probably negative, for example, for probabilities, or so this kind of behavior that the results are kind of untrustable and infeasible in some applications. So yeah, the talk is basically just to go around this subject, introduce the Laplace transformation, which is just a very simple integral, which basically over here we have got a function h t right here, and it is transformed into so-called Laplace domain with the function h star s, and this transformation is via this integral. What is the benefit of using this kind of Laplace transform description? In many cases, the problems can be described in Laplace domain, but cannot be described in time domain. Whenever one deals with stochastic models, the most simple example is the sum of two independent random variable is somehow the convolution. I mean, the distribution of this sum is the convolution in time domain, which is a simple product in transform domain. And all of these background algebra makes the use of Laplace transform very efficient in many subjects. A part of stochastic modeling, it can be applied in differential equations and electronic circuits and so on. So basically, the main problem is that whenever one completes a computation in transform domain, then the result is available in transform domain, but it is of interest to get it back in time domain or the basic original domain. In some cases, there is a way to obtain it in a symbolic way, like symbolic inverse Laplace transformation tools, but in many cases, you need to apply numeric inverse Laplace transformation. So the goal of the numerical inverse Laplace transformation is to obtain a value of a function at a given point based on the transform domain description. So the most efficient ways in recent years for the solution of this problem is the so-called Abate-Witt framework. There are many methods in this framework, which are named over here. And the basic root of this framework is just this simple summation. So what you do, you have got a given set of numbers which are referred to as nodes and the set of numbers which are referred to as weights, and you evaluate the transform function at some points which are characterized on the one hand by the nodes and on the other hand by the point of interest t, capital T. And you just basically evaluate these transform domain functions at a given number of points. You weight it according to these weights eta k, and you just sum up. So I would say that it is not even a tool, it is a very, very simple thing to do. And still the main idea behind the Obatavit framework is that these beta k and eta k weights and nodes are the one which characterizes the procedure, and this is completely independent of the transform function and the point of interest. So basically for each procedure mentioned on the previous slide and each order, you have got a given number of weights and nodes, and you just compute the approximate value of the function according to this summation. So what are the basic idea in the majority of this method? There is a so-called Bromwich inversion formula which evaluates a complex integral. In these methods, which are listed here, various kind of approximations of this complex integral is provided, and in a very strange way it is kind of visible that, for example, this Talbot method, these are the nodes, the beta k values where you evaluate the transform function, and somehow these nodes indicate where the complex integral is. On the other hand, the Euler method is just the one according to this vertical axis, and actually the CME method is also based on a similar kind of set of nodes which are vertically arranged, but the approach behind the CME method is something completely different. The approach behind the CME method is what we refer to as integral interpretation. So basically what you do when you apply this Obatavit framework approach, you just substitute the definition of the transform function, which is just this thing at these points. So by just interchanging the integral and the summation, you are going to have the sum of these weights weighted by this kind of exponential functions. So over here, you have got a so-called weight function, which is integrated over the unknown function. So what the approximation gives you is the integral of the unknown function with a weight function. And basically, if this weight function is just a Dirac impulse, then the approximation is perfect. So in this case, you get back exactly the value you are interested in. So what we intend to do, we intend to find this weight function to be as close to the Dirac impulse as possible. And the way to do this is to come up with a measure. And over here, we use the measure of the coefficient of the variation, which is known in stochastic applications. And we apply this constraint that the weight function should be non-negative. So having solved these problems for various orders, we are having a procedure. Basically, we obtain the weight function. The weight function has got these beta k, eta k weights and nodes, and this already gives us the inverse Laplace transformation approach. So it looks like the weight functions of the CME method is just this continuous line, and the weight functions, which can be also extracted from other methods obtained from different other approaches, are, for example, this dashed line for the Euler method, or this very rather flat for the Gabor method. So basically, over here, we can conclude that this Euler is something which has got even a sharper peak at 0.1, which is of interest, but it has got very significant waves apart of these main peak, while the CME method is something rather peak, but it is rather flat apart of that. So it has got some consequences which I'd like to demonstrate via the tool, and the tool is somehow available at this website. So whenever you just load this website, I would say that's the simplest tool of ever. You just go down, and here is the demo part. What you have is the staircase function, and over here you need to define the staircase function in transform domain, and also you can define the time domain, and in this case the tool plots it for you. So that's how it looked like for order 20. Basically, what you see that this function has to be approximated, and those are the different approximations by the three considered method. The red provides the CME method, the yellow provides the Euler, and the Geiger method is in green, and the original function is in blue. And if you start increasing the order, then you obtain the first difficulty. Basically, the first difficulty, which is more dominant in the Geiger method, is numerical instability. So basically, the Geiger method loses its numerical stability. Okay, I haven't mentioned that this tool uses standard double precision floating point numbers, and the Geiger method loses its numerical stability with this kind of floating point number representation at order 40 in this case. So we just get rid of the Geiger method and we keep checking the behavior. So it's already visible that we have got this kind of waves, which are referred to as Gibbs oscillation in case of the Euler method, and it is not present in case of the CME method. And if you keep going, this kind of oscillation getting more and more dominant, and while it gets more and more dominant with the Euler method, I would say that the CME method gets just closer and closer to the original function. So if you go even more extreme, this Gibbs oscillation gives you practically meaningless result in case of the Euler method, while it is still quite stable. So if I just increase the order further on, what is assumed to be, it is just following more and more sharply the original function. I would say that I need to mention that it is not definitely always the best procedure to apply. If you consider the sine function, then, okay, we went too far. So if you consider the sine function, if you indicate all the other approaches, so that is what the sine function does with this order. It is still quite okay with the Geiger method. And if you start increasing the order, okay, it is not coming. Okay, I don't, okay. So that's what we have with the Euler method at this order. And up to a given order, the Euler method is more correct with the sine function, but whenever this kind of effect of the okay, so this is the effect of numerical instability, but okay, I wanted to demonstrate, of course, something different, but unfortunately I just couldn't get it right now. So that's what we have here. So it seems that the Euler method follows the sine function much closer up to a given point, but if I keep increasing the limit, then it turns out that this Gibbs oscillation shows up, and it gets to be dominant and gets to like over here, this Gibbs oscillation adds up, and it gets to be dominant and modifies the result in a kind of untrustable way. So what is the case with the CME method? The CME method somehow flattens out, but whenever you increase the order, the increased order behavior is approaching the exact one step by step. So basically the key point over here is that the CME method is the one in which increasing the order is going to improve the result, while the other two or whatever other Abbott-Witt framework methods are different from this point of view. And with the increasing order, you face with unpredictable problems, which makes the CME to be the kind of most trustable one. So I think it was all for this short presentation. And yeah, thanks a lot for your attention. And yeah, please visit this website and check the tool.
Thank you very much, Miklos, for the fascinating presentation. We have time for one question. We're a bit stretched with the time. Anyone?
I want to make a comment. Can I make a comment?
Please go ahead,
Susan. Yes, I think this is a very good tool for teaching. I will spread it to my colleagues that use inverse Laplace transform in the courses. So thank you, Miklos.
Thank you.
Miklos, I have a quick question since I don't see in the chat question. So Abbott and Witt moved on to show a range of applications to queuing, for example. Do you see this as a tool that could help in that domain? Are you planning to work on that?
Definitely. Actually, I just put in this, due to some reviewer comment, we put a queuing example also into the paper associated with this presentation. Yeah, there are many practical applications, and yeah, whenever you are using it in stochastic models, it is quite important that the result should be between 0 and 1 if it is a probability, and other procedures does not, I mean, they do not provide this feature. So you might get completely negative probabilities in spite of the fact that the transform domain description is completely correct. Inverse Laplace transformation might result in negative probabilities, which is avoided by the CME method.